Let's talk about the connection of our multivariate results with linear regression. So recall in our linear regression case, if y was a vector, an m by 1 vector, and x was an m by 1 vector, and we fit a model that included a x plus an intercept, the slope coefficient worked out to be beta hat. It worked out to be the empirical covariance between the empirical correlation between x and y times the ratio of the standard deviations. But another way to write this out is and you'll see why I do this in a minute, it's the inverse of the empirical variance of x times and let me just call it sigma squared xy, the empirical covariance of x and y. Okay? And so this is maybe a little bit less convenient to write out because it's nice to work with just the covariance, the correlation, and the two standard deviations. But just think about it in this way right now, where it's the inverse of the variance of the x times the covariance between x and y. Now let's think about our regression example, our multivariable regression example, but let me pull out the intercept. So I have a jn, which jn is just a vector of ones of length 1 times beta naught minus the rest of x, which I'm just going to label x for the time being, and times the rest of beta, which I'm just going to label like that. So I know this is somewhat poor notation, but this is our least squares criteria if we had an intercept, where now I'm assuming my x does not include an intercept. So I just want to relate this back to this formula from linear regression to show that our multivariable regression is sort of the same thing. Actually, yeah, okay, so let me call this vector beta 1, let's say. Okay, so imagine hold beta 1 fixed. Not beta 1 hat. Hold beta 1 fixed. And then we know that asterisk has to be greater than or equal to when we plug in the solution. Well, with beta 1 fixed, the solution to beta naught has to be, let me just rewrite it here just so we can see it, y minus x beta 1 minus jn beta naught squared. So think about just this quantity by itself as if it was a vector. If beta 1 was fixed, then we could think of it that way. Then this is just mean-only regression with this as an outcome, and this is our vector of ones, and that as our single coefficient. Okay, so we could write our beta naught solution as it depends on beta 1 being fixed. Let me write it out that way. That has to just be the mean of this vector right there. We learned that in one of the earlier lectures. So the mean of that vector, right, is going to be 1 over n times y minus x beta transpose times jn, which works out to be y bar minus x bar beta 1. So x bar, by the way, here is, so let's just remind ourselves, y bar is a 1 by 1, is a scalar. X bar is a p by 1 vector of the averages within each of the columns. Oops, I should have a transpose there, sorry. So it's a 1 by p vector of the averages within the columns of x, and beta 1 is a p by 1. Okay, so now let's plug this solution back into our least squares equation, knowing that we can only get smaller if we plug that in. Okay, so we plug that back in, and we get y minus jn times beta naught, which is y bar minus x bar transpose beta 1 minus x beta 1 squared. Okay, so let me rewrite this as y minus jn y bar jn x transpose times beta 1 squared. Let me just double check right here. So remember, x is m by p, jn is m by 1, x is x transpose is 1 by p, so this quantity will be 1 by p. So what you can double check is that this quantity right here is simply the centered version of the columns of x. And we did that in an earlier lecture as well when we talked about centering. So we could write this as, I've been calling y tilde the centered version of y and x tilde the centered version of x, beta 1. Okay. Now, we know that this quantity is minimized with beta 1 hat now equal to x tilde transpose x tilde inverse x tilde transpose y. So I could, as an example, or I could, to think about it this way, is I could multiply by a 1 over n minus 1 here, and then a 1 over n minus 1 here, and that wouldn't do anything because of the inverse right here, that it would just be multiplying by 1. So if we look at this equation now, remember, if I take 1 over n minus 1 times this x tilde transpose x tilde, that's the empirical covariance matrix of the x's. Okay? And then if I take 1 over n minus 1 x tilde transpose y, that's all of the cross covariances between y and x, the empirical cross covariances. So if I go back to my original formula, all the way up here, right? Remember this formula? Let me go down here and write here. Remember our linear regression formula that was sigma hat to the minus 2 of x times sigma hat squared of xy. So what we see is that our multivariable regression coefficient follows exactly the same form as our simple linear regression coefficient. It's the inverse of the variance of the x's times the covariance between the x's and the y's. It just turns out that this is a matrix version, whereas these are all scalars in the linear regression case. Okay, so again, the formula should be